Right, Assalamualaikum everyone. Assalamualaikum and good day everyone. So for this recording, I'm going to share with you how are we going to implement three-phase inverter with 120-degree conduction. So which is this is not too sure which is the slide number, but it's actually the second fixed pulses switching scheme for three-phase inverter. So previously we have looked into three-phase inverter with 180 conduction. So now we are going to look for 120-degree conduction, which is much simpler as compared to 180. Yeah? So first thing, like 180 conduction, first what you need to do is that you need to come up with the construct the gating signal diagram. So first of all, we are going to construct gating signal diagram. Yeah, construct gating signal diagram for 120 conduction. Okay, so for the switches basically, so we have 6 switches. So we have S1, S2 until S6. Okay, and then these gating signal waveform we will divide it into 6 mode, where each of the mode in terms of duration it will consist of 60 degree. So from 0 to 60, 60 to 120, 120 to 180, and until we reach one cycle, which is at 360. Okay. Alright. So for 120 degree conduction, each switch, okay, will conduct or turn on for 100-degree duration in a cycle. Okay. Alright, so we will start with S1 first. So S1 will start to conduct from 0 until 120. When it reach 120, which is already full of the conduction, so it will be turned off, and then it will turn on again until the next cycle. Yeah. So and then we are going to introduce delay. So this is 60-degree delay, right? 60-degree delay from S1. S2 will start to conduct, which is at 60 degree, and then it will continue to conduct until complete 120, which is it will stop to conduct at 180. So 60-degree delay from S2. S3 will start to conduct, which is at 120, and it will continue to conduct until 240. And again 60-degree delay from S3. S4 will start to conduct, which is at 180, and then it will continue to conduct until 300. Okay, 60-degree delay from S4. S5 will start to conduct, which is at 240, and then it will maintain conduction until complete 120, which is it will stop to conduct, turn on at 360. And again lastly for S6, 60-degree delay from S5. S6 will start to conduct at 300, As you can see here, it only able to conduct for 60 degrees. So it has a balance of another 60 degree. So the balance will be placed here. Okay, which is for each of the switch, they must conduct for a period of 120. Okay, now we have, this is what we call as gating signal waveform for S1 until S6. Okay, next step is that you need to determine the switches, the switching for each mode, for each mode. Okay, basically how to do this is that by looking vertically for each of this mode over here. Basically we will have 6 mode. Mode number 1, 2, 3, 4, 5. Again, if let's say that you are wondering why is that we have 6 mode. So in one cycle we have 360 degree. The switching action will take place every 60 degree. So divide by 60 degrees, so you have 6 mode of operation basically. Okay, so we have for mode number 1, which is the duration from 0 to 60. And if you look vertically, you can see the switch that being turned on for that mode number 1 will be S1 and S6. So mode number 2, duration from 60 to 120. Switch that being turned on is S1 and S2. Mode number 3, duration is 120 to 180. The switch that being turned on is S2 and S3. Mode number 4, the duration is 180 to 240. Okay, switch that being turned on is S3 and S4. Okay, mode number 5, duration 240 to 300 degree. And switch that being turned on, if you look vertically, you can see S4 and S5. And lastly, mode number 6, which is the duration from 300 to 360. The switch is S5 and S6. Okay. And then, okay, next, in the next step, which is step number 3, we need to determine the what will be the level for our phase voltage and our line to line voltage. In order to do that, we are going to construct the equivalent circuit. Okay, we will start with mode number 1. Okay, construct equivalent circuit. In each mode, to find phase voltage and line to line voltage. Okay, we'll start with mode number 1. We have S1 and S6 here. Okay. In order for us to draw the equivalent circuit, you need to make sure where this S1 is being positioned in which phase. Is it the upper switch? Is it the bottom switch? And as well as S6. Again, like I mentioned in the previous class, so this is the position of the switch. Okay, S1 and S4 for is the for phase A, S3 and S6 is for phase B, and S5 and S2 is for phase C. So S1, 3, 5, they are called upper switches. S4, 6, and 2 using even number, they are called bottom switches. Yeah, right. So S1 is the upper switch for phase A, S6 is the bottom switch for phase B. So we know that in phase C there are no switches that be turned on, so basically phase C will be open circuit. So basically we have only two resistor, two load, which is for phase A RA, phase B RB, right? Okay, voltage across RA is VAN, voltage across RB is VBN. Okay, this will be the current flow. Okay, so you can see this is just a series circuit. Remember, there are 4 steps that you need to do in order to find what will be the value for your phase voltage and your line-to-line voltage. Number 1, you need to find the equivalent resistance. Okay, so R equivalent will be equals to RA series plus with RB. Okay, so if let's say that you have balanced load, you can represent RA and RB with a single R. Okay, so we represent it by just a single R. So our R equivalent equation will become R plus R, which is you get 2R. So that is the equation for your R equivalent. Okay, number 2, you need to find the current that been flowing in the circuit. Okay, which is I will be equals to your Ohm's law, VDC over R equivalent, which is you substitute the one that you get in step number 1. So your current will be equals to VDC over 2R. Okay, next, we want to find the phase voltage, which is VAN, VBN, and VCN. Alright, so for VAN, okay, it will be I multiplied by RA. Okay, our I is VDC over 2. So if let's say that your R you represent by a single R, RA you will represent by single R. So it will be positive VDC over 2 for your VAN. Okay, how about VBN? Okay, also Ohm's law. Okay, but for VBN, you need to add a negative sign over here because you can see from the circuit you have a reverse polarity between your voltage and current. So you will get negative VDC over 2. Okay, your VCN will be equals to 0 because there is no switch that be turned on for that particular phase. Okay, and last, the fourth step is you need to find your line-to-line voltage. Okay, so your VAB will be equals to VAN minus VBN. Your VAN is VDC over 2. Your VBN is negative VDC over 2. So you will get positive VDC. Okay, your VBC is VBN minus VCN. Your VBN is negative VDC over 2 minus 0. You will get negative VDC over 2. Your VCA, C first, yeah? VCN minus VAN. 0 minus VDC over 2. So you will get negative VDC over 2. So this is the level of your line-to-line voltage for mode number 1. Okay. Then we are going to do for mode number 2. So for mode number 2, okay, the switch is S1 and S2. Okay, mode number 2 is S1 and S2. Mode number 2, S1 and S2. S1 is the upper switch for phase A. S2 is the bottom switch for phase C. So in this case, your phase B will be open circuit. Okay, the step will be the same. Number 1, you need to find the equivalent resistor, which is the equivalent resistor will be equals to RA plus with RC. Okay, this one here, if let's say that you have unbalanced load, you need to make sure that you put the actual value rather than represent it by a single R, because obviously the value of the resistor will not be the same. Okay, so for balance load, yes, you can do that, which is you can represent it by put your RA, RB, and RC with a single R here. So basically, you get 2R over here. That is for balance load, yeah. Okay, and then for the current, so next we need to find what is our currents. We are using Ohm's law. So the actual one will be R equivalent RA plus with RC. So if let's say that you have a balanced load, then it become 2R. Okay, this one here, if let's say that you probably you have unbalanced or you're not sure what will be the value for the load, here will be the balanced load, yeah? So the equation for balanced load. Okay, next we want to find what is our phase voltage. So basically VAN, VBN, and VCN. So our VAN, it will be I multiplied by RA. Okay, just substitute the one that you get in step number 2. Okay. Okay, and then your VBN will be equals to 0, and your VCN negative I multiplied by RC. Okay. Um, again, why is that VCN we have a negative sign? Because of there is a reverse polarity between your voltage and current. Opposite polarity, the direction of your voltage and current, yeah. Okay, so this will be the level for your phase voltage VCN, which is negative VDC over 2. And then we are going to find the next step, which is find the line to line voltage. Okay, your VAB will be equals to VDC over 2. Your BC is VBN minus VCN. Your VBN is 0 minus negative VDC over 2 become positive. Okay, and then your VCA is VCN minus VAN, negative VDC over 2 minus VDC over 2. Then you will get negative VDC. Yeah? So these are the value. Then you be if let's say that you come across with this question, when the question give you the value for your R and your DC link voltage, you can always substitute and find the actual value. Okay, and then in mode number 3 we have S here, S2 and S3. Okay, mode number 3 we have S2 and S3. Okay, which is S3 is the odd number, so it will be the upper switch, right? So it's the upper switch for phase B 135, remember, and then for phase 135462. So C, yeah. Okay, step number 1, find the R equivalent, which is it will be equals to RB plus with RC. For balance load, R plus R, you get 2R. Okay, then step number 2, you need to find the current. Okay, so if let's say that you have unbalanced load, your current will be equals to VDC over RB plus RC. For balanced load, it will be VDC over 2R. Okay, next we find our phase voltage. Okay, VAN, since there is no switch that been turned on for phase A, it will be equals to 0. VBN, I multiply by RB. That's VDC over RB plus RC multiplied by RB, or for balanced load it will be VDC over 2. Okay, our VCN negative here because there is a opposite polarity between the current and voltage. Okay, as for balanced load, your VCN will be equals to negative VDC over 2. Okay, lastly, we need to find our line-to-line current. Sorry, line-to-line voltage. Okay, so for VAB, VAN minus VBN, which is 0 minus VBN is VDC over 2. You will get negative VDC over 2 for your VAB. VBC is VDC over 2 minus negative VDC over 2. You get positive VDC. Okay, VCA it's negative over 2 minus 0. You get negative VDC over 2 for your VCA. Right, next. Okay, let's say we have mode number 4. Okay, for mode number 4, we will have S3 and S4. Okay, S3 odd number, right? So, RB, S4 adalah the bottom switch for phase A, RA. Okay, step number 1, you need to find your R equivalent. So your R equivalent will be equals to RB plus with RA. For balance load, it will be R plus R, which is equivalent to 2R. Okay, next you need to find what is your current. Okay, which is VDC over R equivalent. As for balance load, your current will be equals to VDC over 2R. Okay, next step, you need to find your phase voltage. Okay, VAN, since VRA is being connected to the negative terminal of your DC link voltage. Okay, put the negative here. Okay, so for balance load, your VAN will be equals to negative VDC over 2. Your VBN will be equals to I multiplied by RB, which is VDC over RB plus with RA multiplied by RB. For balance load, it will be VDC over 2. Okay, VCN, obviously there is no switch, 0. Okay, and then the next step, your VAB, okay, negative VDC over 2 minus VDC over 2, you will get negative VDC. VBC is okay, VDC over 2 minus 0. So you get a positive VDC over 2. And VCA is 0 minus negative VDC over 2. So you will get a positive VDC over 2 for VCA in mode number 4. Okay, next, we are going to do for mode number, we are doing just now 3, 4 or 5, eh? Okay, 5. Okay, so for mode number 5, again, we have S4 and S5. S4 is the bottom switch for phase A, S5 is the upper switch for phase C. Okay. The step will be the same. First, you need to find the equivalent resistance, which is RC plus with RB. For balance load, R plus R, which is we will get 2R. Okay, and then step number 2, you need to find the current. Okay, your current will be equals to VDC over RC plus with RA or VDC over 2R. Okay, and then we need to find our phase voltage. Okay. VAN, remember it will be negative because you can see RA being connected to the negative terminal. Easy for you to remember when the load being connected to the negative terminal at the negative sign. Yeah. Okay, as for VBN, it will be equals to 0. VCN, okay, it will be equals to VDC over 2. Okay, fourth step, the last one, you need to find the line to line voltage. Okay, so as for VAB, it will be equals to negative VDC over 2. Okay, VBC is VBN minus VCN. Your VBN is 0 minus VCN is VDC over 2. Also, the answer is negative VDC over 2. And as for VCA, VDC over 2 minus negative VDC over 2. Okay, which is you will get positive VDC. It's actually half multiplied by half, eh? Okay, next, the last mode, which is mode number 6. Okay, the switch that we have is S5 and S6. S5 is the upper switch for phase C. S6 is the bottom switch for phase B. Okay, again, we need to find our equivalent resistance, which is equals to a series, what we call value of RC plus with RB. And for balance load, we replace by a single R, it becomes 2R. Okay, next, you need to find your current. Your current will be equals to VDC over R equivalent. VDC over RC plus with RB multiply with that's it, eh? Okay, no need to do the multiplication. For balance load, it will be VDC over 2R. Okay, and then in the next step, you need to find the phase voltage. Okay, VAN 0, because there is no switch that be turned on for that particular mode, a particular phase. Okay, so your VBN will be equals to negative VDC over 2. Okay, as for VCN, I multiplied by RC. Your current is actually VDC over RC plus with RB multiplied by RC. Okay, so for balance load, it will be VDC over 2R multiplied by R. So it can be cancelled out. Then you get VDC over 2 for your VCN. So lastly, you need to find your line to line voltage. Okay, it will be, okay, VAB will be equals to 0 minus negative VDC over 2 you will get VDC over 2 for your VAB. VBC, it will be VBN minus VCN, which is negative VDC over 2 minus VDC over 2. So you will get negative VDC as your output. And VCA is VCN minus VAN. So VDC over 2 minus 0. So the answer will be VDC over 2. So this is the level for your phase voltage and your line to line voltage for all mode from mode 1 until mode 6. Please, please make sure that you all of you be able to do all this step correctly, and then so that because it will help you a lot during your final examination when you are dealing with question on three phase inverter, right? Okay, so this in this slide basically it show you what will be um the one that we have discussed previously, what are the equivalent circuits and their respective waveform. So basically once we do this analysis from mode 1 until mode 6, okay, we be able to sketch the phase voltage and the line to line voltage using the level that we get in each mode. So basically this is for mode number 1 here, the level for mode number 1 for phase voltage and line to line voltage. This is for mode number 2, as you can see from here. This is for mode number 3. Follow the pointer. Okay, this is for mode number 4, mode number 5, and mode number 6, which is in one cycle. Basically the waveform here is show you in two cycle. You can see from 0 to 4 pi. Okay, the analysis that we did previously is for one cycle because it will be repeat the same things for the next cycle. Yeah. Okay, and then this is with regards to the equation on three-phase inverter with 120-degree conduction. This is for the phase voltage and your line-to-line voltage. Right, so for the phase voltage, as you can see in the equation, so if let's say that we compare, you can do the comparison of the equation between your inverter with 180 and 120. Okay, this part over here is actually finding the amplitude, and the sine n omega here, omega t plus pi over 6 is finding the phase angle. So if let's say that you being asked a question to find what will be the expression of phase voltage in for inverter using 120 degree, so you substitute, it will be 2 VDC over n pi sine n pi over 3 in order to find the amplitude for that particular phase. And then as for the phase angle, it will be sine n omega t plus pi over 6. Basically in terms of amplitude for each of the phases, they will be the same. The only difference is here the phase angle, as you can see. Okay, as for the line to line voltage, basically we extract the using the same equation as in phase voltage, but we add the set 3 over here. You can see from here in order to find the line to line voltage for 120 conduction for of three phase inverter. Okay, right, so I think I will stop up to here first on the theoretical explanation with regards to inverter with 120. So in the next video, I'm going to show you how are you going to solve for the solution, answering the question example that been given in this lecture. Right. Okay, I think that is all. Okay, so thank you everyone.